Hey, AP Chemsters, this is Mrs. Vandelay. This is actually in particular for Danny, Mo, Sam, and Hannah. This is what we did on Monday, March 31st. So I know you're out there enjoying the opening day parade, but this is what the rest of us had to do in class. So we are picking up on KSP, and this is right after the problems that we left off with from the weekend's blank wall. And so problem 13, we're talking about compare the solubilities of silver iodide, copper iodide, and copper sulfate. If you remember from what we did in the first part of this section 15.6, the solubilities is when you solve for X. It is how many moles of the solid, in this case silver iodide, copper iodide, and copper sulfate, will dissolve in 1 liter of solution. So what you'll need to do is set up each KSP problem and solve for X. Compare the different X values, and then you can decide which one is more soluble than the others. Go ahead, pause this now, and when you are done, compare what you did with what I did. All right, so this is what I came up with. I set up each problem pretty much the same, and I found the solubility of silver iodide to be 1.2 times 10 to the negative fifth. And you typically don't forget your units of solubility. It's always going to be moles per liter. Is the KSP that you can drop your units. The copper 1 iodide, you do the same thing, and X equals 2.2 times 10 to the negative 6 moles per liter. And the copper sulfate, I got 0.0078 moles per liter. So if I'm going to compare the solubilities, I'm going to be looking and comparing to the X's. So my biggest X was for copper sulfate. My next biggest X was over here for silver iodide, and my smallest X was over here for the copper 1 iodide. So the solubilities are in that order. Now note a couple things about this particular problem. Notice that the coefficients are all the same. They're all, in this case, 1. And typically you cannot compare KSP values, but in this particular case you can, because your coefficients of your ions are the same. You didn't have to raise any particular thing to a power of 2 or a power of 3. So in the case of these 3 problems, your KSPs are in the exact same order as your solubilities. If you look up here, the KSP for copper sulfate is the smallest, then for the silver iodide, then the copper 1 iodide. So only because your coefficients are the same can you make this comparison of KSPs and solubilities. Now if we look at the next problem, you'll see we can't do that. So here is the next problem. And if I'm going to compare the salts of the copper 2 sulfide, sorry, the silver sulfide and the bismuth sulfide, notice that your coefficients are going to be very different. So we can't look at the KSPs and say, oh, it looks like, yeah, copper 2 sulfide must be the most soluble because it's the smallest KSP. I don't think that's going to be the case. So go ahead and set up each one of these problems and then compare your solubilities. Give yourself a few minutes and then I'll join you again. Okay, hopefully you can read my writing here. If I start over here with the copper 2 sulfide, very straightforward. They're each equal to X, so X equals 9.2 times 10 to the negative 23rd. For your silver sulfide, oops, I left out the S. Excuse me, you have, when you go ahead and dissolve it, dissociate it, you get 2 silver ions and 1 sulfide ion. So you have 2X here and X there. You have silver squared sulfide to the first, and so you end up with 4x to the cubed is equal to 1.6 times 10 to the negative 49. X equals 3.4 times 10 to the negative 10th moles per liter. Over here was the bismuth sulfide. You can see you have 2x and 3x. We're going to have to square this one and cube this one. So you end up with 108 times x to the 5th equals 1 times 10 to the negative 5th. I'm sorry. We'll try this again. We'll end up with 108 x to the 5th is equal to 1.1 times 10 to the negative 73. So when you divided this by 108 and then took the 5th root of it, x equals 1.0 times 10 to the negative 15th. So if you're going to compare these solubilities, you have to look at x. So you'll see the x here with bismuth sulfide is the biggest number, so it's the most soluble of these 3. The next one would be your silver sulfide, so that would be the next most soluble, and really the one that is least soluble out of these 3 would be your copper sulfide right here. So that's how you do that particular problem. Let's go on and see what we're doing next. This is the common ion effect. And this concept is nothing new. We saw the same idea when we talked about buffers, and that is when you had a buffer and you had, let's say, a weak acid, and you also had in solution its conjugate base. You also had the opposite. If you had a weak base and you also had in solution its conjugate acid, how does it affect the pH and the POH? We can say the same thing here. If you have at least one of the ions present to start with in solution, how will that actually affect your solubility of this ionic solid? So let's go through the math and let's see what happens. So in problem number 15, just kind of follow along and see what I'm going to do. So start off with your KSP equation here and set it up like an ICE problem. So no, we do not have any initial calcium ions to start with, but we do have initial fluoride ions. So for every 1 molar solution of sodium fluoride, we end up with the same molar amount of the fluoride ion. So if you start with 0.025 molar sodium fluoride, you start out with 0.025 molar fluoride ion. Remember, your ICE table, you do need molarity, not moles. So let's go ahead and solve it like we always would. And now set up your KSP. Scroll this down a little bit so I have a little more room here. All right, so now what? Well, we have calcium ion we said was X, and we said the fluoride ion was 0.025 plus 2X. Don't forget, you need to square it. Now, do you remember what we did last time that made our life so much easier? We're going to do that 5% rule, and we're going to assume we do not need that. So now our math boils down to squaring the 0.025, and that is 6.5 times 10 to the negative 4th. And that's equal to 4.0 times 10 to the negative 11th. So if you solve for X, and I know the problem didn't ask you to do this, but I think it's very worthwhile to go ahead and solve for the solubility of calcium fluoride without the common ion. So this is with the common ion. Do the same thing without the common ion, just like what we did before. So pause this. Actually work this out below, hopefully still some more room on your paper, and let's compare the answers when you're done. All right, so let's kind of look up here again. So this is what we found with the common ion, and this is what we found without the common ion. And look at our two values. We have 6.4 times 10 to the negative 8th with the common ion, and 2.15 times 10 to the negative 4th without the common ion. What makes the difference? It all boils down to 2 words. It actually is 2 words of the French dude Le Chatelier. So let's go back. If we add this amount of your common ion, how is it going to shift? It's going to shift to the left. What does that mean if it shifts to the left? It means that this will not dissociate as much, that we're going to create more of this product in a sense, or we're going to keep it as a solid longer. It will not dissociate. But without that common ion, there is no shift. So it will not shift to the left. It will not create more calcium fluoride. So that's why this number is bigger. Because you do not have that common ion effect, there is no Le Chatelier stress or shifting going on, and that's what's going on. So if you have a smaller X value, you have less of it dissolving. You have fewer moles per liter dissociating than you do here. You have more of a solid less of the solid. So let's go on to the next one, and let's check out pH. Now, what's going on with pH? Do you remember me telling you way back when that if you have an upset stomach, you might take some Rolaids or some Tums or some milk of magnesia. Those antacids will contain the aluminum hydroxide, magnesium hydroxide, and calcium hydroxide. And the reason why those are not considered strong bases is that they don't dissolve readily. They don't dissolve very well at all. So how can something that doesn't dissolve well work so well in your stomach? Well, obviously your stomach has acid in it. And so this solubility is dependent on pH. So pH and solubility. So it says that the anion X is an effective base where its acid is a weak acid, then the salt will show increased solubility in acidic. So here's the hydroxide, the ones that we're just talking about. We've also seen where the carbonate is also that effective base. It is a pretty basic anion there, so this would work just as well and create, in a sense, the hydrochloric acid. Well, sort of. Not hydrochloric, excuse me, carbonic acid. So let's look at problem number 16. We need to set up just like what we did before and find your dissociation of the equation, and this time incorporate this pH of 9.5. So if the pH is 9.5, then you know that pOH is 4.5, and from there you can calculate your hydroxide concentration, and then it's just like the problem before. So why don't you go ahead and pause this, work on the problem yourself, and then come right back. Okay, so here is the cadmium hydroxide, and I wish my board wouldn't do this when I write, but oh well. And it dissociates into cadmium 2 plus and 2 hydroxides, and I needed to know the concentration of this hydroxide. Well, once again, if pH is 9.5, pH is 4.5, the hydroxide concentration is 3.2 times 10 to the negative fourth. So that's how I got this number here. We're obviously going to add X and add 2X, but look what happens here. When I put this in the equation, I don't need to count this plus 2x, and your math gets so much easier. So don't forget to square the 3.2 times 10 to the negative fourth, and there we go. And so x times this number squared equals 2.5 times 10 to the negative 14th, and x is equal to 2.5 times 10 to the negative 7th, and I'm so sorry, I left off my units, moles per liter, if you want to write that in. All right, so this next one I think is a very good problem. I like this problem a lot. And what you are doing is that you are seeing the effects of the common ion. So the first one is without the common ion. Part B is with your common cerium ion. And then part C is your common fluoride ion. So go ahead and work these problems out and see how you do. So pause this, do the problems, and then check your work. Okay, so hopefully Danny, Sam, Mo, and Hannah, this is what you came up with. You take the cerium fluoride and you dissociate it, and here's your KSP. Don't forget you have to cube your 3x, and so you end up with 27x to the fourth. Divide side by 27, take the fourth root, and you get 7.4 times 10 to the negative fifth moles per liter. That's your solubility without any common ion. So notice what happened here. You have your cerium fluoride with a common cerium ion right here. So when you set it up, you do not need to put in your plus x, you just take that out. So you get 8 times 10 to the negative 16th equals 0.20 times, that's a times, not a plus, 27x to the third, divide each side by 0.20 and divide each side by 27, take the cube root, and you get 5.3 times 10 to the negative 6. Now compare this number with this number. What do you notice? You notice that your solubility dropped, okay? Without the common ion, you had more of the cerium fluoride dissolving. With the common ion, you have less of it dissolving. Why is that, folks? 2 words. Le Chatelier, that's 2 words. If I add more of the fluoride, it shifts to the left, so I have less of the cerium fluoride dissociating. Real quick, because I only have a few seconds left, here is the value. You get 1 times 10 to the negative 13th when you have the common fluoride ion. And again, solubility dropped. Why? 2 words. You got it. Le Chatelier. See you tomorrow.